Hey guys, thanks for tuning in to Simtech channel. This is going to be a short tutorial on demonstrating variable sizes in C programming. And this tutorial here is already part of our series on C programming, learning by coding, where we talked about the variable sizes. Now, I just want to expand quickly a little bit on this topic, just to demonstrate exactly what do we mean when we talk about C programming variable sizes. As you see in the beginning, I showed this microcontroller here. This is a Nucleo board, okay, from STM Microelectronics. Now, this board here have got an onboard chip, this big one here. So this chip here, if we scroll down, there is different type of them. It's an STM32 from the F3 families. So if we come on this table here, it's telling us the various flash memory sizes. So we've got a 64 kilobyte, 128, 256, 512, 1 meg, and so forth. Now, this flash memory is very important for an embedded system engineer who got the sole role of programming this Nucleo board for consumer electronics. For instance, this is a type of a non-volatile memory that you can erase data and reprogram the data later, and it will keep the data even if you switch off your device, you power it. So this is like for storing important data, like what kind of example can we take? As an example, let's say you have a fingerprint scanner machine like this as a security system to allow people to get in. Now, this fingerprint scanner have a microcontroller that is controlling the whole system. And the microcontroller will have a flash memory that will have data stored into the system, so that every time someone put in the finger, they are able to recognize the fingerprint and then open the door. So this data is stored in there whether you switch off the device, disconnect and plug it back on, the information will not get lost. So those are the type of information that are stored into your flash memory for your embedded system. But now, as you can see here, you've got limited space. You don't have a lot of space. So you're talking about 512 kilobyte for this specific one here. So what it means is, for anyone who's busy programming this microcontroller here, you have to take care of the space available to you so that you are able to work within the allocated space and you don't run out of space. And this is where C programming data variable sizes come into effect. Now, I've written this program here just to quickly to demonstrate to you guys. If I run this program just one time here, as you can see what we're getting here, the size of int is 4 byte, which is a 32-bit. So I'm declaring a variable int a, okay, and it's got a sizes of 4 byte, which is 32 bits. And a long will then have also a sizes of 4 byte, and a long will then have a size of 8 bytes, which is 64 bits, and a long double will have double the size of a double, so that gives you 64 byte, which is 128 bits of data. So what it means, in contrast to what I showed you guys earlier here, so for every integer or variable you declare, it's taking a 4 bytes of space. So if you have a chip that only got 512 kilobyte of memory space, which is a lot, but remember, for every byte where you're declaring variable, there is 4 bytes going. So if you have your program with a lot of variable, which in a normal embedded C programming code, there will be a lot of variable declarations and variable definitions and all of that. So which means a lot of your space will be going as you declare and add new variable into your code. So you have to keep that in mind. Now, the other important things about variable sizes is the amount of data they can actually hold as you declare them. Now, if I may just run this program one more time, as we can see here that an integer is 4 bytes and 32-bit, what it means here is that 32-bit integer will basically mean that it's 2 to the power 32. That's what it means. And this number, if you run this number on your calculator, so this number will be 2 to the power 32. So it's giving me a very large number. So that's basically, it's 429,496,7,296. It's a big number. As you can see, it's a big number. So we're talking about 1, 2, 3. So that's about 4 billion. So, and this number is also in a negative. Okay. So this is a positive of this number, and you can also have the negative of the number. And from here, you can see that a 64-bit would also carry a large number. Now, let's say, since we know that an integer that is 2 to the power 32, so that's a 32 bits size, and it stores this 4 billion. Now, if I then say, okay, well, I'm going to declare a variable here, and I'm going to say, since I have already declared a as an integer, and then I'm going to make an assignment, and I say a is equal to 20 billion. So let's go 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is 20 billion. Now, after assigning a the value of 20 billion to hold, knowing too well that the variable a declared here as an integer can only hold a value, okay, that's got the size of up to 4 billion, as we can see here. So that is the only variable size that a can hold as being an integer. But now I've assigned a to hold 20 billion. Now let's see if we will be able to print this 20 billion on our screen without losing data. So I'm just going to call in another printf function here, and I'm gonna just go into a new line and then say test. Okay, and then from here I will then print. Okay, then I'm gonna say %d for integer. Okay, then I'm going to pass a here. Now, since a have been declared as an integer, and then I've passed a value of 20 billion into a, I should be able to print 20 billion if a is indeed capable of holding the 20 billion. Okay, now let's run it and see what do we get. Okay, now look what I'm getting here. Test, I'm getting a negative number. Okay, so let's just make this a little bit neat. So we're going to say here a is equal, and then let's go into a new line. So that will be more pretty to read from our console there. Okay, so now we're getting a is equal to minus, it's a negative number. So it's telling us that the variable a that we declared earlier as an integer could not hold 20 billion. So what happened is it overflowed into a negative region. So that means the a here is not the correct variable for us to hold this big number for us. So we need a different type of variable. So let's stop this and then move on to now change. Instead of putting, okay, now let's just prove the concept is correct. So I'm going to remove 1 0. So it's no longer 20 billion. And then we're going to run it again. This time around, we should be able to print the 2 billion because we know that a is able to hold 4 billion. Okay. Now let's print again to see if a can indeed hold 2 billion as an integer. Let's run the program and see what we get. You can see now a is happy to hold the 2 billion. in contrast to the 20 billion that it was unable. So, well, what do we then do if we need to hold the 20 billion? Well, the problem is simple. We have to change a variable type. So we need to increase from an int into a long or a double. Okay, so we know that from this table here, if we can see here, well, a long is 8 byte. Okay, a long is 8 byte. So a long is then what? Well, let's just print again and see what we're going to get on our screen here, what we've been getting. So a long is 8 byte. Okay, so that gives us a 64 bits, and we know that 64 bits is a big number. 64 bit is not child's play. So that is basically your 2 to the power 64, and you don't even want to print that. So if you take 2 to the power 64, and that is now giving me 1.8 10 to the power 19. So this is a big number, and clearly this number can hold a billion. So where did we get that? We get that from a 64 bit. So which means either a double or a long is going to do the job for us. So now let's see what do we have here. So variable C, okay, is a long, and D was declared also as a double. So if we then change here, we say then D, okay, is equal to 20 billion, okay, not 2 billion. And then we must come here, so it's a double. We must come here and we print. Let's just copy this, and we change this to be a D, and then we need to change its LF for the double variable data type, and we need to change this one here into a D. Now when we run this, we should be able to print the 20 billion into our double variable. Now let's just run it and see. Okay, so we are printing D is equal to 20 billion. Okay, we got a lot of decimal places. This is because it is a double, so it's a precision variable type. So we can limit the number of comma by doing a dot 2. Okay, that means we only need 2 commas after. So now we're getting the 2 comma, but our 20 billion is coming intact. So we can even change this number into 9 billion. And we know that the 64 bit can hold also the 9 billion. So everything is okay. We can even make it 90 billion. And we print, we're still going to get the 90 billion. We're not losing anything because the double is a correct variable type. Now, if we don't want the decimal places, we can then just change this into the long. So that is a C. So we must just put C there. Okay. And we pass C here. Then we need to change the format specifier here. So that's a LLD for long. So we need to remove the dot there because this will just print as a number without decimal places. So when we print this, and as you can see, we are printing our 90 billion without any problem, without losing any data. So this is how critical variable sizes and data type are important in C programming. So please guys, if you find anything useful in this tutorial, don't forget to subscribe to Simtech channel and stay tuned for more tutorial like this, and give this tutorial a thumbs up. Until next time, cheers.